Well, good afternoon, people. How are you doing?
Good.
Good. I hope people find my marking style to be acceptable. I don't generally put any comments on the paper if the problems are correct. And if they're incorrect, I'll give a very brief statement about what's wrong. So I've caught up on the marking so far. Marked homeworks 1 and 2. Homework 3, I think, is due on Friday. And I think homework 4 is due the Monday thereafter on the 22nd. All right, what's this? Holy moly. Okay, I think people should be able to see my screen. Is that true?
Yes.
Any questions from last day while we're just waiting to go? Okay, it's 12:35, so I'll begin. Yeah, so we're working on a cell spreadsheet model, which should allow us to calculate the volumetric energy density of a lithium-ion cell based on knowledge of the various components in the cell. So I started on this last time, but I was unable to finish. And I don't really want to go through the pages that I was considering before again, just make a few comments from this slide. So the idea is you specify a positive electrode material, and you know its specific capacity, and you know the thickness of the electrode that you want to make, and you know the porosity of the electrode that you're going to create, the binder content and the carbon black content. Okay. And what you want to do is then design a negative electrode that's balanced, meaning it will have the appropriate capacity to accommodate all the lithium that comes from the positive over to the graphite. That's the idea here. And that graphite will have a certain thickness based on its porosity, its specific capacity, its binder content, and its carbon black conducting diluent content, okay? So then you can figure out exactly the capacity per unit area of the positive and the matched negative. You know the average voltage of the cell based on your positive electrode material choice, and you can calculate the energy density of this cell, the volumetric energy density. So we went through a few pages of this stuff, and we got to here, I think. And then what we have to do at this point is equate the capacity per unit area of the negative electrode to the capacity per unit area of the positive electrode, where we've already solved, we already have expressions for these sigma P, WP, and QP. And if we do that, we get this big equation here. So typically we assume that the active weight fraction of the positive and the active weight fraction of the negative is the same. So for most of the cells, most of the lithium-ion cells with graphite negative electrodes, these active fractions are about 96%. Okay, and they're usually very close, so just assume they're the same. And then what you're trying to do is, given the thickness of the positive and knowledge of everything else in this equation, just solve for the thickness of the negative electrode. And that's what we go ahead and do. And then you have to calculate the capacity of the cell, okay? So if you think about what is the capacity of that electrode stack, this electrode stack here per unit area, so per centimeter squared, for example, it's twice the capacity per unit area of the positive times 1 minus the fraction of irreversible capacity of the negative. So this may confuse you a little bit. Where does this come from? And I'll just spend a moment on my document camera showing you that this makes sense, okay? So I'll go to the document camera for a minute. How do I do that? Do you see my document camera now?
No, we do not. We're still on the slideshow.
Really? How about now?
There we go.
Okay, so just to show you why the specific capacity is what it is. Let me get straight here. Excuse me, why the capacity per unit area of the stack is what it is. This is voltage versus lithium and capacity. And the positive electrode will go up sort of like this and come back sort of like that. And the negative electrode for a balanced cell go out like this to the same point, and then come back and typically have a larger irreversible capacity than the positive. So the cell capacity is this, you know. So you have the capacity of the positive. This is QP, but you have to subtract from it the fraction due to the irreversible capacity of the negative side. So we say that's QP times 1 minus the fraction of irreversible capacity. So if this is 10%, then this would be 0.9 QP. 0.9 QP. And that is a factor of 2 because our electrode stack has got a double-sided positive electrode. Okay, does that make sense to people?
Just to confirm, this is the first cycle of the battery?
This is the very first cycle, but then afterwards the cell will cycle. I'm going to use a black pen or a red pen. Afterwards, the cell is going to cycle like this. Along the red curve. The graphite is empty at this point. So you cannot fill the positive all the way. This is an anode limited cell. When the positive is empty, the graphite's full. So you're cycling 0.9 QP.
Thank you, that makes sense.
Okay. I'm going to share my screen again. Where was I? This. Okay, you should be able to see my screen again. Okay, so then you have to figure out how much of this electrode stack can fit into the cell. Okay, so you know the capacity per unit area of the stack. Let's see where my mouse is moving. And if you know the volume of the jelly roll and divide by the thickness of the stack, that tells you how much area of stack you can fit into the cell. And the thickness of the stack we've worked out before, all right? So the cell capacity is the stack area that fits into the cell can multiplied by the capacity per unit area of the stack, this thing here. And the cell energy is the cell capacity times the average voltage. So all these things make sense and they're easy to work out. Now the other thing that's really useful to calculate is something called the stack energy density. It's very useful to calculate, and it's independent of the cell design that you ultimately select, be it a pouch cell or a cylindrical cell. And it's just the capacity per unit area of the stack divided by the thickness of the stack. That gives you the capacity per unit volume of the stack. Capacity per unit area divided by thickness is capacity per unit volume of the stack multiplied by the average voltage. That's the stack energy density in units of something like watt hours per liter. And there you go. So all these things that you need to calculate stack energy density, I've just listed them here again on this slide. So in your homework 4, you have to calculate stack energy densities for a few things. So I wanted to just show you the way that lithium-ion cells have evolved over the years by using a spreadsheet model that incorporates what we've shown here. So I'm going to switch over to an Excel spreadsheet now, and we'll have a look at that. So let me share that screen. Okay. Can you see my Excel spreadsheet here?
Yep. Yep.
Okay. So what I have here on the left side is the thickness of the positive electrode, single side coating in centimeters. So 0.004 centimeters is 40 microns thick, and it goes up to 90 microns thick. And then on the negative side, this is the corresponding thickness of the negative for a balanced cell based on the assumptions that I've made with respect to the electrode materials. So let's talk about what we made. Positive density is 5.08. Who knows what positive electrode material that is?
lithium cobalt oxide.
Right on. You guys all calculated it in homework 1. The binder density is 1.4 grams per cc, so that's PVDF. The carbon density is for the carbon black. It's about 2 grams per cc. And the negative electrode is graphite. Its density is 2.2 grams per cc. So these are all the things you need to put into the spreadsheet model. And then you say, well, the active fraction. We're working here in 1991. Okay, we're starting in 1991. In those days, the active fraction in the electrodes was about 90%, and the binder percentage was about 5, and the fraction of carbon black was about 5. And in those days, you couldn't get thin separators. They're about 30 microns thick, so 0.003. And the lithium cobalt oxide was only charged to maybe 4.2 volts, so it's about 140 milliamp hours per gram. And the graphites were decent. So what this represents here is the first lithiation capacity of the graphite. So this would be based on an irreversible capacity of 7%. The reversible capacity of this graphite would be 360 times 0.93. Okay, so it's not that great a graphite based on today's capacities, where this would be more like 390 on the first lithiation. And the porosity of the electrodes is 40%, because in the old days, the calendar rollers that people had were not enormous, you know, to really compress the living hell out of the electrodes. And in those days, you couldn't get super thin copper. It was about 20 microns. Aluminum was about 16. And the irreversible capacity of the graphites were around 7% even then. So you wind up the jelly roll and you stick it in a can. Well, I'm working on an 18650 cell. So the volume of the can, I've listed up here, it's pi times r squared. So an 18650 cell has a radius of 0.9 centimeters, and its height is 6.5 centimeters. So the volume of the can is 16.54 centimeters. But that's the outside of the can, okay? And you have to have the headers at the top, insulators, top and bottom. There's a hole in the middle of the jelly roll where the winding starts, so it's not completely filled. So the volume of the jelly roll in those old days represented about 55% of the available volume of the can, okay? And you can take a look over here at the stack energy densities in watt hours per liter, and you'll notice that they increase as the positive electrode thickness increases. And this is because the volume fraction of the inactive components, the separator, the aluminum foil, and the copper foil, becomes less and less the thicker you make the positive electrode, and the negative electrode correspondingly. And the capacity of these 18650s, you know, about 1200 milliamp hours back in those days. Okay, so pretty low capacity. Today, a good 18650 is pushing 4 amp hours, really. So pretty crappy. So we're going to see what we have to change here to make a better cell, and the impact the various changes have, because it's quite interesting to do that. Now, there's one other thing that's shown here, and this is the estimated diffusion time for a lithium atom to go from one electrode to the other, from the back of the negative to the back of the positive. And the reason that I calculate this, and it's described in a slide in the PowerPoint, is because if you make the electrodes too thick, like you would say, oh, look, I can just keep making the energy density bigger and bigger the thicker I make things. Well, then it just takes too long for the lithium to diffuse through the electrolyte from one electrode to the other, and the cells have got terrible rate capability. These cells, because the porosity is so big, you know, that's 1800 seconds, it's half an hour. So these things could easily run at a rate of 2C. So really no issue there. And this is a very approximate number. It's just sort of like a guideline that I use for myself. Okay, so let's, oh my God. Am I back in the meeting? I was kicked out for a minute.
Yeah, you're back now, but we lost you for like a minute.
Yeah, is my PowerPoint, I mean,
Yeah, I can still see your Excel sheets.
okay, good, the Excel sheet's still here. Okay, so now we're gonna be a Japanese engineer and say, okay, let's improve these cells and see what we can do, all right? So for a long time, everything stayed with lithium cobalt oxide, but the active fractions started to increase. So maybe they went to we'll go all the way to 0.96, okay? Whoops. And that means we have to reduce the binder fraction to 0.02. And the carbon fraction to 0.02. And the separator thicknesses start to come down by about 0.02, so 002, sorry, 20 micron. And people started charging the 4.3 or 4.35, so that was about 160. And better graphites came along. We'll go all the way to 390. And the electrode porosities dropped probably to 30%. And you can see the stack energy densities now are up around 800, whereas before they were in the 500 range. And the copper foil became thin, and today it's 8 microns, so 0.0008. And aluminum is thinner than this, probably about 0.0012, 12 micron. Irreversible capacity is about the same, right? And people learned how to limit the size of the headers and all the wasted space within the can. So the volume of the jelly roll increased probably to about 11, maybe 11.5. A typical good number is 70% of the volume of the can is filled with the active material, okay? So this gets you up to about 2,600 milliamp hours for an 18650. And this is what you do, right? You just pack more material in the can and things become better. So how do you get to 4 amp hours? Well, you change over to NCA or NMC 811. So the positive density goes to about 4.8. That's not in our favor, but it is what it is. And the active fraction and so on all remain about the same, but now the specific capacity goes to about 210. And the porosity drops about 0.2. And now we're up at 3,200. And then if you go out and you actually measure the can of an 18650 cell, you'll find they're not 18 millimeter diameter. They're more like 18.6 millimeter diameter. So people are cheating every way they can. So this radius has to be increased to 0.93. And why won't that enter? That gives you 17.6, which means we can, to get our 70% filling, we can go up here, about 12.5. There we are. And now we're at 3,500 milliamp hours in the cell. You know, so these are the tricks that you play. You just keep jamming more stuff in the can. You cheat on the can diameter, and you end up with close to the 4 amp hour mark. You know, so playing with a spreadsheet model like this is really a lot of fun, because you can see the trade-offs that you make. And if you look at this diffusion time for the lithium to go from the back of one electrode to the other, you know, here it's about a half an hour for fairly thin electrodes. So this would be, if you want to have a more power cell design, you would make thin electrodes. If you want a more energy cell design, you would make thicker electrodes, but you pay the penalty that it takes longer to charge the thing. And these are approximate numbers, just with a hand waving model. So anyway, this is a very, very handy way to deal with new battery technologies. You know, somebody comes along and says, oh, you know, my cell's the greatest thing since sliced bread. Well, you can put it in a cell spreadsheet model and figure out, you know, what the stack energy density is and what a typical cylindrical cell energy storage in watt hours or capacity would be. Okay, so any questions about this?
I had a small question.
Yeah.
The ratio for the volume of the jelly roll to the volume of the can, when we changed the diameter there a little bit, it didn't really change that ratio. So does that ratio stay the same for 2170s as well?
Well, it did change it. This used to be 11.5, the volume of the jelly roll, but when I increased the diameter of the can, I increased the volume of the jelly roll to 12.5 to keep this at 0.7. You know, when you go to a larger cell format, like a Tesla 4680, the big fat one that they're going to be making, the volume of the jelly roll compared to the volume of the can will be bigger. Maybe it'll be 0.8. I don't know.
Okay, because they also have that like really large center too in that biscuit tin or whatever they called it. They seem to have a larger center hole and whatnot, but
Well, it could be the case, but as you know, the volume in the center is way smaller than the volume in a ring at the outside once things get really big.
yeah. Okay.
Yeah, so this is, you know, the real number that you want is the stack energy density, because then you don't have to make assumptions about the filling fraction of a particular can. And that's what, you know, when we are working on new cell designs here, for example, using lithium-rich positive electrode materials like Ron was doing, we calculate stack energy densities and compare back to standard lithium-ion chemistry. So this is really the thing you want. It's an independent number of cell design. Yeah. Any other questions about this? Okay, so on homework 4, you'll have a chance to play around with this for lithium-ion cells and also for a liquid metal cell that a company called Ambry is producing now. All right, so I'll go on to the next topic now. So I'm gonna stop sharing this screen, start sharing another screen. Whoops, wrong screen. Where's the right screen? This one? Yeah, here. Oh, yeah, this is it. Okay, so can you see the front page of this
Yep.
Electrolyte PowerPoint? Okay, thanks. Yeah, so we've talked about positive electrode materials. We talked about negative electrode materials. We talked about cell design. We talked about separators, but we haven't yet talked about the electrolyte, its properties, and the solid electrolyte interface that's made when the electrolyte comes in contact with the reactive electrode materials. We haven't talked about the diffusion of lithium in the electrolyte in any detail. We haven't talked about what happens when a large current flows in a lithium ion cell, what happens to the electrolyte concentration in the cell as a function of position and something called electrolyte depletion. And we haven't talked in detail about diffusion of lithium into the intercalation materials. So this PowerPoint has just a whole grab bag of stuff in it. And a lot of these ideas, you know, they're treated nicely in McKinnon's thesis, chapter 7, which I've emailed to you. And I recommend that you have a read of that. Okay, so let's get started. Yeah, so if you think about the electrolyte, there's certain requirements that it must have. It has to be able to transport lithium quickly enough during charge and discharge. So this means a high ionic conductivity or a high lithium diffusion constant in the electrolyte. It needs to be stable in the voltage range of the cell. Now, what does that mean? It's a sort of it means kinetically stable in the voltage range of the cell. The electrolyte will react on the surface of the charged electrode materials, the positive and the negative, but it has to form a passivating layer on both electrodes that still allows lithium ions to transport through the passivating layer. It should have a high dielectric constant to be able to dissolve electrolyte salt, and it should have a wide liquid range, meaning both in temperature and in salt concentration. So these are the main characteristics of the electrolyte. And to be stable in the voltage range of the cell, it completely eliminates the use of water as the electrolyte, unless you play some very fancy tricks that Chung Yin Yang is an expert on. And he might give us a lecture later in the course on those fancy tricks. So the common non-aqueous solvents that we use in lithium-ion cells, and really these three are the main solvents that are used. Oh God. I seem to have disappeared for a moment.
You're back now. Yeah, we lost you again for a minute.
I don't know what's going on. I'm in the Dunn
Yeah.
building. You would hope that the internet's good here.
It looks like my internet is kind of slow in the building as well. I'm not sure why.
It's
Okay.
kind of weird because I don't notice a gap.
Yeah,
You
I'm not
just go,
noticing a
"Oh,
gap
shit."
either.
Okay, anyway, so I was talking about the most common electrolyte solvents are ethylene carbonate, ethyl methyl carbonate, and dimethyl carbonate, and their structures are shown here. And in the typical way of organic chemistry, hydrogens are not shown at carbon vertexes. So there are 2 hydrogen atoms here and 2 hydrogen atoms here. So EC has 4 hydrogen atoms not specifically shown. Ethyl methyl carbonate has 2 hydrogen atoms on this carbon vertex here, not shown. And all the hydrogen atoms are shown on dimethyl carbonate here, okay? So if you look at these things, EC has a high melting point. It's a solid at room temperature, so it's not going to be too good as a battery electrolyte. But it has a huge dielectric constant, so it can dissolve salts. And at 40 degrees C, it's very viscous. And we'll learn that the higher the viscosity, the lower the ionic conductivity. So you want low viscosity solvents for, you know, high ionic conductivity. And then if you look at ethyl methyl carbonate, it melts at minus 53 degrees C. So that's great. It's never going to freeze on the Earth typically. But its dielectric constant is really terrible. So it's difficult for EMC to dissolve salts, especially at low salt content. We'll learn more about electrolytes that only contain ethyl methyl carbonate or only contain dimethyl carbonate later on. They're quite interesting. But it has a low viscosity, and that's good. And dimethyl carbonate has a melting point. I don't think this is right. I think it's more like minus 8 degrees. I should have checked this table. But anyway, it's very near 0 degrees C. And it again has a crappy dielectric constant, but it's even less viscous than EMC, so that's good. So typically what you do is you blend these things together so that you can make a mixed solvent that has a acceptable melting point, acceptable dielectric constant, and acceptable viscosity. And that's the strategy and why we use mixed solvents in lithium-ion cells. If there was the ideal solvent, we wouldn't use mixed solvents at all, but there isn't the ideal solvent.
Yep.
And you know that, and this is kind of like very fortunate. It's very fortunate that you can do this and get away with it. If you know, if one of these things didn't exist, it would make our life a lot more difficult as a lithium battery scientist. Someone had a question.
Yeah. So for the property of the EMC and DMC, they are relatively close. So why would for one of our electrolyte blend, we need that 5% of EMC?
Yeah, that's a historical component that Panasonic puts in their cells. So I think it's added in there just to lower the freezing point a bit, because with EC and DMC mixture, the eutectic is around minus 10 C. But when you add EMC, you can drive that down more. So it's to help prevent electrolytes partially freezing at temperatures that you may encounter in wintertime.
Okay, thank you.
Yeah, so this is a graph that shows you what happens when you mix electrolytes together. So like I said, typically you would combine EC with either EMC or DMC or both. And in the mixture, their respective bad properties are minimized while retaining the desirable properties. So let's take a look. If we take EC and mix it with DMC, so over here would be 0 DMC, and over here is 100 DMC. And this line is the dielectric constant. It starts around almost 65 or so, and goes all the way down to that of DMC. So it's pretty much a linear variation. And then this curve shows the viscosity. Which drops as you add DMC. We'd have to actually look at the paper to know what curve A and curve B represent. But this is the idea, right? You pick a blend that gives you properties that are good enough for what you want. So electrolyte salts. There's a few common salts. And this is a table that's a little bit dated. The most common one is lithium PF6. And it's very cheap at the moment. It's very soluble in electrolyte. The only possible issue with it is its thermal stability is not that great, and also it reacts readily with water to make HF. Lithium BF4, not used too much. This lithium bisoxylato borate is called LiBob. It's a common electrolyte additive, especially in cells with lithium manganese oxide spinel. And this is called lithium bistrifluoromethane sulfonamide, or the short name for it is LITFSI, TFSI. And again, this is used as an additive in certain cells. So the reason they're used is solubility, stability, reasonably safe, reasonably cheap, don't perturb the SEI, and they can aid in SEI formation. But really the main salt is lithium PF6. Okay, so now I want to start talking about the solid electrolyte interface. I mean, everybody that's in my group and in Mark Overbeck's group and maybe in Lucas Swan's group has heard about the solid electrolyte interface, but it's really worth talking about it in sort of detail. So I want to start by talking about aluminum, okay? If you take pure aluminum powder, and it's in a glove box, then it's very fine powder and it's pure, and you bring it into the air, it will react so violently in the reaction aluminum plus oxygen goes to aluminum oxide that it heats enormously, 1,000 degrees C or more. In fact, Alcan, Aluminum Company of Canada, makes solid propellant rocket fuel, which contains pure aluminum powder. I think somewhere in our lab is a metal can of solid aluminum powder that I requested from Alcan. Pure. And the can is labeled something like, "Do not open in air." Okay. So aluminum reacts with air violently, but yet you can walk around and see pop cans everywhere and aluminum canoes, and they're absolutely stable. They're not bursting into flame, and they're not flying into the atmosphere as a rocket. And the reason is what happens is on those large objects, there's a reaction between the aluminum and the air, which makes an aluminum oxide film. And once that aluminum oxide film gets somewhat thick, it stops the further reaction of the aluminum and the air. It's a passivating layer, okay? Now, if you take lithium metal or lithiated carbon, lithiated graphite, and you throw them in propylene carbonate or ethylene carbonate, they will instantaneously react and form a layer of reaction products on their surface. And that, fortunately, that layer of reaction products is very similar to the aluminum oxide on aluminum that hinders, doesn't stop completely, but hinders further reaction and slows it down to be very, very slow in most cases. Now, the free energy of reaction between lithium metal and ethylene carbonate is something like minus 50 kilocalories per mole. It's very close to the free energy of reaction of hydrogen and oxygen goes to water, which is rocket fuel. So it means that if this reaction is allowed to proceed to completion, you will get vast amount of energies released. And if you expose passivated lithium, so that means lithium that's been in propylene carbonate and it's still within propylene carbonate or still within ethylene carbonate or in battery electrolyte, you expose it to very high temperature, the solid electrolyte interface on these materials contains organics, and it's not thermally stable up to temperatures over 130 degrees C or so. And the reaction will just continue, and you'll have a self-sustaining runaway thermal reaction, okay? So the passivating layer on lithium metal or lithiated graphite is not thermally stable to enormously high temperature, and that's one of the reasons we have the safety issues associated with lithium-ion cells if you're not careful. So it's really a miracle that this solid electrolyte interface forms and that lithium can transport through it, because lithium atoms are in the reaction product, so it's like a solid electrolyte. So any questions about that little story? Okay, so what is the solid electrolyte interface? This layer consists of insoluble products from the reaction of intercalated lithium with the solution, the electrolyte solution. This layer acts as an interface between the negative electrode particles and the solution and has the properties of a solid electrolyte. It's an ionic conductor and electronic insulator. It's a passivating film which almost entirely prevents reactions between the intercalated lithium and the electrolyte. And this layer was called the solid electrolyte interface by Peled in this very, very famous paper from 1979. And from Peled's paper, there's a picture of the solid electrolyte interface where, you know, each of these A, B, C things are labeled as different chemical compounds. So polyolefins are things like polyethylene, polypropylene. Semicarbonates are things like lithium alkyl carbonates, which would be part of these things. So this is a very heterogeneous mess, and it makes it incredibly difficult to study. Okay, it's incredibly difficult to study and figure out exactly what this thing is. Our laboratory and many laboratories around the world have spent a lot of time trying to understand the solid electrolyte interface. You can figure out what chemical species are in here and what elements are in there, but knowing exactly how they're arranged and how the lithium ions transport through it is very, very difficult. So one thing you have to realize is that as this layer is formed and continues to form, as this gets thicker over time, lithium atoms in the cell are irreversibly lost. They end up incorporated in these reaction products in the SEI. And like all chemical reactions, this goes faster at higher temperature. This is one of the reasons why lithium-ion cells lose capacity faster at higher temperature. This is a really nice paper by Mengyun Nai. She comes from Brett Luck's group. Mengyun, after she finished her PhD, she came here to do a postdoc. And she spent a lot of time characterizing the SEI on graphite and found that there was this, oh my goodness.
LEDC.
Yeah, it's LEDC, but what is the name? Lithium ethylene dicarbonate. Yeah, lithium ethylene dicarbonate. So you see the ethylene in the middle and the two carbonate groups on the either end. So this was a really sort of a breakthrough paper, but then later on, some other researchers came along and said, well, wait a minute, we made this lithium ethylene dicarbonate pure, and it doesn't conduct lithium ions at all. So how could it be a component of the SEI? And they proposed that it was really, you know, something else other than this, but related. So you can make progress sort of understanding the components of the SEI to some degree. Mengyun, by the way, is either has started work for Tesla or is about to start work for Tesla. So we'll be interacting with her again, at least my group, in the upcoming months. This is a paper that talked about using an additive, propene soltone, as an additive in lithium-ion cells. The idea here is that when you put an additive into the electrolyte, often the additive reacts with the charged electrode surfaces first, and its reaction products control the chemistry of the SEI. So when you include a sulfur-containing additive in the electrolyte, you get sulfur atoms in the SEI, and that changes it very differently compared to in the absence of sulfur-containing materials. So there's lots and lots of papers in the literature from many, many groups that talk about the impact of additives on the chemistry of the SEI. Okay, so what's coming next, I think, is incredibly cool. And this is a simple growth model for SEI growth. And it can be formulated very similarly to the growth of oxides on metal. So there's a giant article. See, look at the page count from 231 to 316, and reports on progress in physics by this guy Lawless, who reviewed numerous models of oxide growth on metals, which he followed a huge variety of rate laws. And, you know, like I argued at the beginning of this section on the SEI, when you put aluminum into the air, aluminum oxide forms, the oxide layer gets thicker, and the oxide growth more or less comes to a stop. The same is true when you put lithium metal into electrolyte. The reaction products form, the SEI layer thickens, and the reaction products the reaction more or less stops. So you would think the same kind of rate laws could be used to describe SEI growth that are used to describe oxide growth on metals. And that's where I'm going to start on Friday, because we're sort of at the end of time. And we'll go through this. And it's really quite cool how incredibly simple models can match the experiment pretty well for the SEI on graphite. So if there's any questions now, it's a good time before we stop.
Hi, Jeff. I have a question about the solvent choice. So at the beginning, we said that water would be unstable at these voltages, and that's why we use organic carbonates. But how did we make that jump to specifically organic carbonates instead of other types of organic solvents like ethers or esters or other things?
Well, that's a great question. I would say the answer to that question is trial and error. I can remember when we were at Molly Energy at the beginning, it was like, okay, what do we try? You know, I remember a rack of cells that James Dudley, the electrolyte technician, filled with dimethylformamide, okay? So they have lithium metal wound up with molybdenum sulfide, positive electrodes, wound in a AA can. You fill them, you seal them, and then he just put them down on a pad of paper in a cell rack. It looked like sort of like an egg carton where the cells are just nicely arranged. And he went to have lunch in his office that looked out on his lab through a window. And after a few minutes, the whole rack of cells was on fire. He came running to get me. He said, Jeff, the whole lab's on fire. So we had to spray it with the Lithex fire extinguisher, which shoots out graphite powder onto this thing, and it just made the whole lab this black powder mess, you know? And this is how you learn. This solvent you're not going to use, right? So dimethylformamide, DMF, you're just never going to use it. And if you look at some of David Hall's papers on fast charge, you know, you take every low viscosity solvent that you can imagine, and you mix it in with the standard electrolyte solvents, and you see if you get any kind of electrolyte that basically works. And you learn that some of them are just terrible because they react with the lithiated graphite and so on. So, yeah.
So for the additive that is used in the previous slide, like the sulfur-containing additive, when they form the SEI, does all the LEDC change? Like, I mean, does the SEI on graphite is solely formed by this additive, or there's still some EC involved in this formation process?
Yeah, it depends, right? We talk about additives that are that dominate the SEI composition, and then we talk about SEI modifiers that modify it a little bit. So there's two different types of things that happen. You see it in the electrolyte reduction curves of cells. If you see a peak altogether due to the additive that then eliminates the EC reduction peak, you say that additive has controlled the SEI formation, right? There would be no LEDC at all. Yeah, but anyway, just so go back to Aniko's question, it really was a question of the whole, why do we pick these three? Because they don't react, they work well.
Hey Jeff, are we going to talk about the passivation on the cathode? I don't know if it's called SEI as well, but
yeah, a lot of people call it the CEI, the cathode electrolyte interface. It's a lot more nebulous, a lot less understood. I'm not going to talk about it in this class just because there's not a lot known about it really.
got it.
And actually, for many types of cells, once the cathode electrolyte interface is pretty stable, all the capacity loss in the cells is due to the negative electrode lithium inventory loss on the growing SEI. So, it turns out that certain classes of electrode materials that lead to high energy density cells have issues at the positive electrode, but more modest positive electrode materials like LFP don't really have a lot of issues on the positive side. So I'm going to just focus on the negative side.
Hey, Jeff.
Yeah.
If you have, let's say, a lithium foil and a graphite electrode that is lithiated, like fully lithiated with the same amount of lithium that would be in your lithium foil, and for whatever reason, the lithium foil and the lithiated graphite have similar surface area or surface roughness, which one would you expect to be more reactive with the electrolyte?
The lithium metal is more reactive with the electrolyte at elevated temperature. And
Even if the
because,
graphite has the same amount of lithium intercalated in it?
yeah, it's a question of how fast can the lithium get to the electrolyte to react, right? And you always have this solid state diffusion step in the lithiated graphite particle that you don't have in the lithium metal.
Okay.
Yeah, Alex has some nice movies, of lithiated graphite electrodes put into water. They just kind of fizz and they don't do too much compared to high surface area lithium metal, which is like an explosion. All right, well, I'm glad there were questions. That's great. I'd like to have more throughout these classes. And that's a good place to stop for today, so we will. So I'll see you all on Friday. Bye.
Thank you. Bye.
Thanks for the class.